Yeah, in the name of the Almighty, the Compassionate, the Merciful. Again, we pursue the subject of differentiation. In our last lecture, actually, we spoke of the existence of the derivative, and we set out conditions for its existence. And we said that the derivative, in fact, was a limit of some fraction, and this fraction contains as the numerator the difference between two different values of y divided by two different values of x's in an interval, for example. And if this limit occurs, then we say that the function is differentiable at a particular point. Suppose the function is not, in fact, given in the explicit form, y is equal to f of x, but suppose it is given in an implicit form. How can we obtain from this form dy by dx? Or, for example, suppose you have a function f and you wish to obtain the derivative of the inverse of that function. Like, for example, you wish to obtain the derivative of sine minus 1x, or, for example, the logarithm of x, which is the inverse function of the exponential function, etc. How we are going to do that? In this lesson, in fact, we are going to display these kind of notions, like the derivative of the inverse function, along with other notions as well, like the derivative of implicit functions and parametric functions, and so forth. So we shall speak in fact, first about the derivative of the inverse function. The derivative of the inverse function, it includes, of course, first the derivative of the inverse function as a notion, and then when it comes to the composite function, we shall also speak about when the function is in the form of a composite function of between two functions, one interior and one exterior, like the form f of g of x, in which we spoke about when we consider composite function, and then implicit functions as well, and parametric forms. And then finally, we end up with repeated differentiation. And now for the derivative of the inverse function, there is a theorem actually which relates the derivative of f minus 1 with the derivative of f in this form. D by dy, it states that d by dy of f minus 1 of y at some y equals to f of a, it is equal to 1 over d by dx of f of x at x, the point x is equal to a. In other words, it relates the derivative of the inverse function at some point in the range of f together, it relates it to the derivative of the original function at the point x is equal to a, which belongs to the domain of f. So in fact, from this, one can calculate directly the derivative of the inverse function. In this point, f of a does actually, because it belongs to the range of the function. In other words, we want to obtain the derivative at the point p of y and x, rather than the point x and y. Here, this belongs to the f, whereas here it belongs to f minus 1. And this is actually our main course that we are going to follow now. The theorem states the following. If f is differentiable at a, in the domain of f, then its inverse function, if it exists, of course, is differentiable at f of a, which belongs to the range of f, and it is given from the formula, the following formula, which is df minus 1 at y is equal to f of a is equal to 1 over d by dx of f of x. And actually, this is the formula that we have just written. This formula, actually, you can write it in another way, which is equivalent as well. You can say that dx by dy at y, certain value of y in the range of f, is equal 1 over dy by dx at some x in the domain of f. Suppose, for example, we wish to apply this to the function x squared minus 3. This function x squared minus 3, you can draw it, the graph in this form, and you wish to calculate the derivative at the point, for example, 2 and 1. This is the original function, y, and this is x. So in fact, we are looking for what? We are seeking to calculate the tangent of this angle alpha. This is actually a dy by dx, because this is dy, and here this is dx. So in fact, when you calculate dy by dx, what you do is you calculate the slope of the tangent at what? At a point, the point 2 on the graph of f. This is dy by dx. But this is not what you want. You want to calculate dx by dy on the graph of f minus 1. Where is the graph of f minus 1? That's exactly what we're going to do now. You have two options. Either you calculate f minus 1. This is the first option. From here, you have here y is equal to x squared minus 3, and therefore x is equal to y plus 3 under the square root. And since here you have x greater than or equal to 0, then you keep the positive sign of the square root. And from there onward, you can calculate dx by dy at the point what? At the point y. Where is the point y? The point y is equal to 1, which belongs to the range of f. So either you say at the point y in the range of f, or you can imagine that you have another function, f minus 1 of y, and this function f minus 1 of y, you imagine that the y-axis now becomes horizontal and the x-axis is the vertical one, and you have to calculate the derivative of such function at the point, at which point? At the point 2 here, 1 and 2. Becomes here the x-axis, I'm sorry, not the x-axis, but the horizontal axis is y, and in which case you want to calculate this at the value y is equal to 1. So all you have to do, you differentiate this, and now we know it very well. This is y plus 3 to the power half, so you got half divided by y plus 3, and you substitute y is equal to 1 to get 1 over 4. 1 over 4 is what? 1 over 4 is the slope of the tangent at the point 1 on the inverse function, or it is 1 over the slope here at the original function, because the slope here is what? The slope here is dy by dx of x squared minus c is equal to 2x. At x is equal to 2, it gives 4. So in fact, one is the reciprocal of the other. In other words, if this slope here is equal to 4, then the slope of the tangent of the inverse function becomes equal to 1 over 4. This, in fact, one way or one option which you can follow. But the other one, which is simpler, is what? Is you apply the theorem. Instead of calculating f minus 1, all you have to do is you say dx by dy at the point y is equal to 1 is equal 1 over dy by dx at the point x, which is what? Which belongs to the domain of the original function, which is x squared minus 3. So in fact, if you differentiate this this expression here, you get 2x, and then you substitute x equal to get 1 over 4. In fact, both are similar. The only advantage of this method is that you need not calculate the inverse function. In fact, in some situations, you will not be able to do that. If you have a function which is cumbersome or tedious to calculate the inverse, for example, polynomials of third degree, you cannot invert it, and therefore you have to follow the theorem, which is better. Now, suppose we do this. Here we follow, exactly like we said, here you calculated the inverse function, f minus 1 of y, and then you substituted like we did at y is equal to 1. But rather, if you if you follow the second line of or the second choice which we mentioned, which is the theorem, in fact, all you have to do is to calculate dx by dy is equal to 1 over dy by dx, and you directly obtain the derivative of the inverse function in terms of the original of the derivative of the inverse function directly in terms of the derivative of the original function, which is of course much simpler. The reason why we recommend the student to follow this second approach is that sometimes you would not be able to calculate or determine the inverse function. For example, like a function of this sort, y is equal to x cubed plus 2x plus 1 minus 1. This function, in fact, you would not be able to calculate f minus 1 of y. In other words, you solve it to obtain x in terms of y. So what we do, instead of this, we first, you want to calculate this at y is equal to, that means on y which lies on f minus 1, the first of the pair which lies on f minus 1. In other words, we slide in the domain of the inverse function or the range of f. If you want to use the theorem, you have to calculate first the point which lies in the domain of f. So if you put here x, y is equal to 2, it corresponds actually to the point x is equal to 1, because when x is equal to 1, you get y is equal to 2. So now you have directly your theorem, dx by dy at the point y is equal to 2 is equal to 1 over dy by dx at the point x is equal to 1. So if you differentiate this function, you get 3x squared plus 2. You substitute x equal to 1 to obtain 1 over 5. So 1 over 5 now, as we have seen, we have it's easy to calculate it instead of calculating, or it's impossible, as a matter of fact, for this example to calculate the inverse function. What in fact you do? What do you do here? This is exactly what you do. You have two circles here like this. One represents the domain of f, and one represents the range of f. And you have here a point A, and you have here a point f of A. And this is the function f, which brings A to f of A, and rather this is the point f minus 1, which brings f of A into A. So what you do exactly, what you do here is that you say, this is briefly what you say. You say dx by dy at the point y is equal to f of A is equal 1 over dy by dx at the point A, dy by dx at the point A. So you differentiate, you get the what? This is dy, this is the change dy, and this is the change dx. And you wish to calculate dx, this change over this change, if it exists in the limit. So it's equal to 1 over this change in the limit. So the theorem, in fact, allows you to get quickly the derivative of the inverse, which is dy by dx. That's it. That's the value 1 over 5 that we just calculated. In fact, sometimes we have functions not in the form of f of x, and you wish to calculate f minus 1 of x, but rather in the form of the inverse function already. Like, for example, you wish to calculate the derivative of sine minus 1x or logarithm x. Would you consider this as the original function or the inverse function? Of course, it's the inverse function. Why? Because if this is the original function and you wish to calculate the derivative of the inverse function to this one is sine, and you know very well the derivative of the sine, which you already calculated, to be cosine. So, in fact, we don't want the derivative of the inverse of this one. We wish to calculate this derivative here. So, instead of having the theorem in a form or expressed in a form in which this is A and this is f of A, you might as well consider this is the point x equal to A, and this is the point y is equal to f minus 1 of A. And here you have similarly the same thing. This is f and this is f minus 1, and you wish to calculate what? You wish to calculate now dy by dx. At which point? At the point x equal to A. So this is the function now in the inverse form. So it's equal to what? Dx by dy. At which point now? At the point f minus 1 of A. And this, in fact, is a better way of dealing or handling, or I would say expressing the theorem in the form that you allow the function to be put automatically in the inverse form. This, in fact, allows you to calculate logarithm of x. Suppose now you wish to calculate the derivative of logarithm x. You have two options. Either you write it in this way: x is equal to e to the power y, and you calculate dx by dy, which is equal also to exponential, same exponential, and therefore dy by dx is equal to 1 over e to the power y, but e to the power y is equal to x, so you get 1 over x, and this is in fact your derivative. Well, there is another way of doing it, is that you can rely actually on the theorem. The theorem tells you that if y here represent the inverse function, y is equal to f minus 1 of x, then you can in fact use the derivative at the point x is equal to A, or x in this example, in the range of the function f, or in the domain of f minus 1. So in fact you have dy by dx at A is equal of 1 divided by dx by dy of f minus 1 of A. So in fact, coming back to our equation here, you can write down d by dx of the logarithm x at the point x, which is in the range of the function, is equal over to 1 over d by dy of what? Of the exponential function with respect to y, of d e to the y. At which point of y? At the point, in fact, y is equal to the logarithm of x. So you are making use of the fact of the theorem. You have here df minus 1 of x with respect to x is equal to 1 over d by dy of what? This is the inverse function of the original function in terms of y, of e to the power y at the point y, which belongs to what then? To the range of the inverse function, which is f minus 1 of a, or it is logarithm x. In other words, you maintain log x, ln x as the inverse function. So in which case you get it directly. D by dy of e to the y is equal to the y. At the point y is equal to ln x, which is equal directly to 1 over e to the ln x, and you know very well that this is equal to 1 over x for x greater than 0. This actually is the way you can do it. Of course, this is simpler, but this you make use directly of our final expression. Now, if you wish to do the same thing on the for example, inverse function, so you say d by dx of sine minus 1x is equal to 1 over d by dy of sine y at the point y is equal to sine minus 1x. So you get directly here what the derivative of sine is equal to cosine. So cosine what? Cosine of sine minus 1x. But the cosine of something is equal to the square root of 1 minus sine square. So you get here directly 1 minus sine square of sine minus 1x. And you know this is the inverse of one another. Therefore, sine of sine minus 1 is equal to x. And therefore, you directly obtain 1 over 1 square root of 1 minus x square. Of course, you can do it otherwise. You can write y is equal to sine minus 1x. And then get x is equal to sine y. And then you get the derivative of dx by dy in the form of cosine y. And then you write this at the square root of 1 minus sine square y. And again, dx by dy, dy by dx is equal to 1 over the square root of 1 minus sine square y. But then sine square y from here is equal to x. So you get this in the form 1 minus x square. So you realize directly that the other expression actually is much faster. You get it directly by applying the theorem instead of rotating around. But of course, this is much simpler. And as a matter of fact, this is the way students prefer to do it. If we gather all of these functions, now you have established that the derivative of ln x is equal to 1 over x. Of course, if it is log, then it is in this sort. The sine minus 1x, now we found it already that it is equal to 1 over square root of 1 minus x squared. And of course, here, the domain of this function is modulus x mod x less than 1, because the sine minus 1, yet it existed from minus 1 to 1 closed. The derivative cannot be obtained at the point x equal to 1 or minus 1. And same thing with the cosine minus 1, and the tan minus 1, the cosec minus 1, and the sec minus 1, and the cotangent minus 1, etc. But you have to remember something, that for the sec minus 1 here, in this expression here, we have 1 over x times the square root of x squared minus 1. But we said this before, in fact. We said that if you like to maintain the fact of the sec in this form, in other words, here you have 1, and here you have minus 1, and here you have pi by 2, and here you have pi, then actually you see that the derivative is always positive. The slope of the tangent is always positive. And therefore, you have to write it in the form 1 over mod x square root of x squared minus 1. So in fact, the one that you have here, we've chosen a different course. We chose this other curve, but it's up to you. And actually, this is the one that the calculators actually use. And same thing with the cotangent. Before we said this is the cotangent in this form from 0 to pi, but we wish to have it as an inverse function of a cotangent, and the cotangent you wish to have it this way. In other words, to have it to have the domain pi by 2, from minus pi by 2 to pi by 2. Why? Because the tan itself, this is the tan minus 1, and the tan minus 1 has as range from minus pi by 2 to pi by 2. So you wish to maintain the same domain for both tan minus 1 and same range, I suppose, same range for tan minus 1 and cotangent minus 1. And this is why if you invert this cotangent, you get something like this, and here something like this, and here is closed and here is open, because this is not an inverse, is not a one-to-one function. But it's immaterial. Here you find that the slope is negative, and here as well the slope is negative. So actually both give the same expression here of minus 1 over 1 plus x squared. If you have the sine hyperbolic, we know very well that it's a form of a logarithm, as we said before, and if you differentiate it, you get similar expressions. You may find it in any book. And same thing with the cosec hyperbolic or secant hyperbolic or cotangent hyperbolic. They all work out similarly in a similar way. These are trivial examples which you can obtain. Now we move to another notion. Now we spoke about the inverse of a function, the derivative of the inverse. Now what about composite functions? If you have a function of the form f of g of x and you wish to calculate the derivative with respect to x, how would you do that? The best thing is that you assign another variable u, for example, is equal to g of x, and we thank Leibniz for his thoughts. Actually, this is the idea that was brought about by Leibniz. Leibniz, what he did, he said that you can manipulate like algebra, in the sense that if this is equal to u, so d by dx of f of g of x, you differentiate with respect to d by du of f of u times du by dx. So in fact, what you get here is f prime of what? F prime of u, which is what? Which is g of x. In other words, you get the derivative of the composite function with respect to g, not with respect to x, times du, in other words, which means g dash of x. And of course, the domain of this derivative, you'll find it, it's the intersection between the domain of the composite function f dash with j and the derivative and the domain of j prime. So this is how you do it in the notation of Lagrange. But actually, there is a much easier notation. You show it this way. You have now f of u, and you wish to differentiate this with respect to x. So you call it this way. df by dx is equal to df by du, thanks to Leibniz, times du by dx. So in fact, all you have to do is to assign u to g of x. And this is actually the best way of doing it. So the chain rule tells you the following. If y is equal to f of u and u is equal to g of x, and g is differentiable at a, while f is differentiable at g of a, of course, then the derivative of the composition at a is equal to dy by dx at a is equal to differentiate it first with respect to u at g of a, then you multiply it by the derivative of u with respect to x. In fact, you can this allows you to manipulate many functions to obtain the derivative. Suppose, for example, you have a function of this sort, e to the power square root of x. This is a composite function. Composite function between two functions, which are e to the power x and square root of x. Now, what you do is that the best thing is that you assign t square root of x to t. In other words, you substitute square x of t, x is equal to t, and then you have dy by dx is equal to what? Dy by dt times dt by dx. Now, dy by dt, since y is equal to e to the t, you get e to the t to the power t as well, times dt by dx. This is the simple function, 1 over square root of t, and you end up with what? E to the t, which is e to the square root of x times 1 over 2 square root of x. Of course, some students say, why should we do it this way? One memorize it directly. You differentiate this with respect to x, and then you multiply it by the derivative of square root of x. But this actually doesn't make you fall into mistakes on one hand. On the other hand, it helps you actually decompose the composite function into two straight elementary function. Look here, this is an elementary function. Y is equal to e to the power t, as well as t equals square root of x. So actually, the composite function, which is rather complicated, not very much, but it can be decomposed into two elementary functions. Same thing here. You have a composite function of many functions. You have x squared plus 1, the square root of this, and then the square root of 1 plus this, and then you have the tangent of this. So actually, what you do, the best thing is that you do the following substitutions. You have first, you substitute x squared plus 1 is equal to t, and then you have square root of t plus 1. You assign it to v, and then you have 1 plus square root of t, which is v. Now you have the square root of v, which is you call u, and finally 10 of this square root is equal to 10u. So now you have dy by dx is equal to dy by du times du by dv times dv by dt times dt by dx, and they all, as you notice, cancel out to so that dy by dx remains. In fact, doing it this not only correct, but also it allows you to decompose any complicated, cumbersome function of this sort into into 4 elementary functions. This is an elementary one that you know the derivative. This one as well as the tangent and the square root of v. So as a matter of fact, you start by decomposing the complicated, rather complicated function into a set of elementary functions from which you can proceed further onward to calculate your derivative. And this is your derivative. Now you have some theorems. If f is differentiable at a at a point a, then the derivative of x to the power n. This is one application of the chain rule. Since you can assign f of x to u, you have here d by dx of u to the power n is equal to the d by du of u to the power n, which is n u, which is f of x to the power n minus 1, times the derivative of f, which is f dash of x. Same thing, suppose you have a square root of f of x to the power 1 over n. Same thing. Suppose you have the square root, the modulus of f of x. You can put f of x equal to, so you get the derivative of modulus u with respect to u, which we saw it before in our last lecture, is equal to mod u over u. In other words, mod f of x over x, times the derivative of f, which is f of f dash of x. So in fact, the chain rule allows you to manipulate the derivatives of many functions. Here we try to calculate the derivative, for example, of x to the power x. How can we do this? In fact, this you can do it through many ways. One of them is that here you have the function x to the power x. You can do it in many ways. First of all, the easiest is to take the logarithm of both sides. You get logarithm y is equal to logarithm of this, which is equal x ln x. So the derivative of logarithm y, this is a composite function, is 1 over y. In terms of with respect to y times y prime, which is dy by dx, is equal to what? The derivative of this, the first one derivative times ln x plus x times the derivative of ln x, which is 1 over x, and you end up with what? Y dash is equal to y, which is x to the power x, times here 1 plus logarithm x. This is one way of doing it. The other way is you can write x to the x in the form e to the ln x, which is x to the power x. And then you apply your chain rule directly. The derivative of this function is what? Is the same function, which is x to the x, times the derivative of this. What is the derivative of this? Of u. Here, the first one is ln 1 times ln x plus x times the derivative of ln x, which is 1 over x. And you get the same, actually, thing. There is a third way of doing it. You can have it as e to the, you calculate the differential times x plus dx. And you end up with the what? With y plus dy. And then you subtract e to the x ln x. And here you do your approximation, like we said it before. You expand ln x in the term of ln x plus dx over x, and then ln x here, e to the this is equal to what? Is equal to e to the ln x times e to the ln x. Here, all you have to do is that you manipulate this in the form of logarithm x plus this logarithm, logarithm 1 plus dx over x. This is a Mercator series of logarithm x, which is equal to what? Dx over x, because logarithm of this is logarithm x times plus logarithm 1 plus dx over x. And this is equal to logarithm x plus logarithm 1 plus dx over x. And in fact, this one is equal to the Mercator series, dx over x approximately. So in fact, this is your approximation. So in fact, we have 3 methods of doing it. And actually, the easiest of the 3 is this one, the first one. And it not only that, but it allows you also, for example, to deal with function of this sort. Y is equal to, for example, sine cubic x times 1 plus x square divided by 1 minus x cube. For example, times e to the power x plus 1 to the power 4. How can you do this? The best thing is that taking the logarithm. Logarithm of ln y is equal to what? Logarithm of this minus this. Logarithm of this, logarithm of a product is equal to this, logarithm of this plus logarithm of this. And the logarithm of sine cube is equal to 3 times logarithm of sine x plus the logarithm of 1 plus x square. Minus 3 times the logarithm of 1 minus x, and finally minus 4 times the logarithm of e to the power x plus 1. And then you proceed forward. For example, the first one is easy because it's 3 logarithm with respect to u. The derivative of ln sine x is 1 over sine x times the derivative of sine, which is cosine. It means 3 cotangent, etc. And you keep on going this way, times the derivative 2x, etc. And when you finish, here you get 1 over y, y prime. When you finish, you multiply all by y In other way, you multiply by this expression. Of course, you can imagine if you do it otherwise, it's going to be very difficult. Now, finally, suppose you wish to speak about derivative of implicit functions. Implicit functions of the form dy by dx, you wish to calculate derivative from this expression here. It's easy. All you have to do is that you derive this with respect to x, both sides. So from the left-hand side, what you do, you assign this to u. Same thing. You differentiate this with respect to cosine xy, which is sine xy, times the derivative of xy with respect to x, which is equal to what? Is equal to y plus x dy by dx. This is derivative of the left-hand side. Or add the derivative of the right-hand side is simply 1 plus dy by dx. And then when you take dy by dx on one side, you end up with an expression like this. So in fact, this is the way how we do it. You always assign a separate variable u in order to manipulate and to simplify your derivatives. Again, if you have your function in the form of a parametric function, this is a parametric function. So the derivative, and you wish to obtain dy by dx directly, thanks again to Leibniz. Dy by dx is equal to what? Is equal to dy by dt, and this is like this. Dy by dx is equal to dy by dt divided by dt, dx by dt. So in fact, you differentiate first f dash divided by g dash. And if, for example, suppose you want to calculate dy by dx of this, like this, of this expression. So we have dy by dx is equal to derivative of this with respect to t divided by the derivative of this to obtain minus cosine t. Now, we spoke about single differentiation. Suppose you have to differentiate twice, 3 times, etc. So these are actually the variables or the symbols which we use. Again, these are the symbol of Lagrange. This is of Bernoulli, and these again of Lagrange. So if you put dot, then it's Newton. But these are actually the eternal ones of Leibniz. And you wish to obtain the derivative of, for example, a product of two functions. This is the best way of doing it. Of course, you can do it by hand. Once, twice, etc. But you can follow also a theorem of this sort. This theorem, the derivative, it tells you the derivative, the nth derivative of a product of two functions is equal to the binomial expansion of what? Of as if you are expanding by binomial. The nth derivative of this one times this one without derivative, plus nc1, the combination of n with c1, times the derivative of this n minus 1 times the first derivative of this one. And you keep doing this unless the last term it will be f of x times the nth derivative of g. In other words, you follow the Pascal triangle. These are your coefficients. You add up each time to get a new coefficient. These are the binomial coefficients. So you can actually, all you have to do is that you substitute the Pascal triangle into your binomial, into your expansion of the product of the nth here, the nth derivative of a product of two functions. Suppose, for example, finally you have, for example, y is equal to x cubed sine x, and you wish to obtain, for example, the third derivative. All you have to do, this is the first derivative of f, this is the second, and this is the third, and this is the first derivative of g, sine gives cosine, and again gives minus sine x, and again of minus sine x times minus cosine x, and you wish, and now what is the third derivative? You start by what? The third derivative of this one, 6, times the other one without derivative, as it is, sine x, plus 3c1 times what? Times the second derivative of f, times what? Times the first derivative of g prime. Of course, the third would be what? 3c2 times the first derivative of f prime times the second derivative of what? Of g double prime, etc. And you go forward. You have here, for example, 4 terms, and this is the way how things go. With this, actually, if we try to speak about our lesson and summarize what we said. In fact, we spoke of many issues. The first issue is the issue of the inverse function. And we said that you have two options. Either you calculate your inverse function, and then from then onward, you calculate the derivative of the inverse function. And this is one way of doing it. But it has one simple disadvantage, is that you may not be able to extract your inverse function. And actually, this is the case in many situations. Or your inverse function is given in the inverse form, like, for example, logarithm x, or sine minus 1, or sine hyperbolic minus 1. These kind of functions are in the form already of the inverse function. And you wish to obtain the derivative of this function. Not of its inverse, of course, because It is known, like the sine is known, and the sine hyperbolic is known. So what you do, you try to manipulate, you try to use a theorem which allows you to obtain the derivative of the inverse function. In fact, this is how it goes. Either you do it this way, or you have here two sets. This is x, and this is f of x, which is y. So you get the derivative of dx by dy at the point f of a. This is a, and this is f of a. At the point f of a is equal to 1 over dy by dx at the point a. This is the theorem. Dx by dy is equal to 1 over dy by dx. This is what? This is the tan of the angle, tangent of the angle of inclination of the tangent with respect to the x-axis at the inverse function, whereas this one is the tangent, 1 over the tangent, or the cotangent of the angle of the original function at the point a. And this is the same, of course. If this is 5, this is 1 over 5, etc. This is 5, and this is 1 over 5. So you get at the end the two opposite to each other. This is one way of doing it. And this is the function f, and this is the function f minus 1. The other way of doing it, this if you can put x in the terms of y. But if you have y is equal to sine minus 1 logarithm minus 1, and you want to put it in the form which is amenable to the inverse function directly, you can call this a, and this is again f minus 1, and this is f, and in this case this becomes f minus 1 of a, and the same thing goes as well. This is y, and this is x, so you get dy dx by dy, dy by dx at the point a is equal to 1 over dx by dy of the inverse function, which brings here y is equal to f minus 1 of a. And this actually allows you to calculate, for example, the inverse of sine minus 1 x. Again, if you find difficulty in understanding or in assimilating such notions, all you have to do is that you try to manipulate simple methods. There is no need to actually use an expression of this sort. If you find difficulty in working with it, you may use, as you have seen. Suppose, for example, you want y is equal to cosine minus 1x, and you wish to calculate the derivative. You can write it this way: x is equal to cosine y, and this is actually more amenable not only to understanding, but also you may not fall into errors. And this you get dx by dy is equal to cosine gives a minus sign, and again this is equal to minus the square root of minus cosine square x, but cosine square x here, because since x dx by dy is equal to cosine y, I'm sorry, so this is y. So cosine y is equal to square root of 1 minus x square, and therefore dy by dx is equal to minus 1 over the square root of 1 minus x square. Of course, here modulus x should be less than 1. So actually, this is one way of doing it, and this is the easiest way. Again, the idea of the logarithm is vital, to use always the logarithm, and because sometimes your functions are in the product form or in a quotient form. For example, f of x over g of x. And you wish, for example, to obtain the derivative. The best thing is to take the logarithm. You get logarithm f of x minus logarithm g of x, especially if this is complicated, and this one too. So you decompose your function, because you know this, the derivative of this is equal to 1 over f prime, 1 over f, I'm sorry, times f prime. And this one is as well, 1 over g times g prime. So actually it's easy. And then this one gives 1 over y prime. So if you multiply by y, which is f of x of g of x, you get directly all this term multiplied by f of x over g of x. So actually the logarithm permits you to do many things. At the end of our lecture, I wish to remind you again that this site, this lecture of this lecture, as well as the one which has preceded it, and the one which we're going to pursue, giving on the in Rome here, all pertain to the project MEDNET-U administered by the Consortium Nettuno of Distance Learning. And you can, as a matter of fact, subscribe. And later on, there are going to be as well chatting and forum. And all the exercises related to these lessons are also put there, which you can find exams corrected, and you can find all the tables of these functions and these these lessons and all the files of these lessons concerning the tables, the results, the theorems are well fed into this site. And at the end, hoping to meet you again. I thank you for your attention, and I wish you good luck, and thank you very much.